All right, you guys, welcome back. Here's what we're going to do. We're going to find the area, bounded by x equals 2 to the y and x equals y squared. Now this is going to be crazy, so don't panic, don't freak out, all right? Now you can almost think of these as being f of y equals 2 to the y and g of y equals y squared. Now this is tricky because we probably haven't played around with a whole lot of functions of y yet, but think about it. All that it does is it takes the independent variable from being x and the dependent variable from being y, and it reverses them. It flips them. Okay? Now let's take a look at what these functions look like. But before we do, let's talk about some tricky stuff. If you don't know what these functions look like, it's very difficult for you to figure out which function is bigger and which function is smaller. It's also very difficult for us to be able to figure out when they intersect. Remember, intersection was really important because those were the places where it crossed over. So if I set 2 to the y equal to y squared, I mean, you may be able to look at that and say, wait a sec, okay, I know when y equals 2, right? Then I get 4 and 4, that's a solution, right? And wait a sec, I'll bet when y equals 4, does that work too? 2 to the 4th is 16, 4 squared is 16. Awesome. So I've got those two, but there may be another one. All right, so let's sketch this graph out. We're going to sketch it out over here, and then I'm going to blow it up over here. So 2 to the y, what does 2 to the y look like? Now, if push absolutely met shove, you could actually change these. You could turn this into y equals 2 to the x, and y equals x squared if you're freaking out. But the problem is you may not always be presented with that kind of a function visually on a test or in a homework problem. So you got to get used to what these things look like. All right, you ready? So here comes 2 to the y. This is x equals 2 to the y. Now I'm going to exaggerate something, and it's going to get a little bit tricky, but don't freak out. All right, y squared looks like this, and then 2 to the y catches it. Remember how big 2 to the y gets? I mean, if you double something and then double something and then double something a whole bunch of times, then you end up, I'm not very good at drawing these things like this. I don't have much practice. Now look at what we got here. Let's talk about this for a sec. This is going to be x equals y squared. All right? So what I'm talking about is, let me change colors real quick. I'm talking about the region defined between these two curves. Actually, I might be able to do this one. Now I'll exaggerate it over here. I'm talking about the region between these two curves. Now look at what's going on here. These two curves, they intersect at this point, they intersect at this point, and they intersect at this point. But literally, dealing with curves that look like this is going to flip our understanding of how functions work. That's why it's such a great deal. Now, let me see if I can sketch this thing. Whoops, I want to use black again. See if I can sketch this thing so this is just a little more exaggerated. You know what? I like the way this works, and I can draw over the top of it. All right, you ready? Let's draw some action. What does our action look like? Well, over here, look, our action was these vertical rectangles. Our width was delta x. It was a change in x. That's important, right? That's the width of our subinterval. When we took an infinite number of infinitely thin slices of action, it went to delta, or it went to dx, correct? But now we're talking about functions of y. So now our action looks like that. It's a sideways rectangle. And instead of having a width of delta x, it has a width, quote unquote, of delta y. Likewise, up here, look close. Look at that. This thing's going to have a width of delta y, and it's going to have a height, quote unquote, of something else. Now let's look close. What is this quote unquote height of our action? Well, isn't it this x equals 2 to the y minus x equals y squared? Now you may say, wait a sec, Ripley, something's crazy here. X equals y squared is above 2 to the y right here. It's taller than it. Yeah, that'd be true if we were talking about functions of x. Remember, f of x is defined as the vertical distance. But these are functions of y. So now we're talking about horizontal distances. Functions which are further to the right are greater than functions which are further to the left. So this distance right here is going to be defined as 2 to the y minus y squared, isn't it? Now, again, 2 to the y is further right. Therefore, it's bigger. It wins. than y squared. Now over here, that flips, doesn't it? Now, from whatever point this is, and we'll name those here in just a sec, from whatever point this is to whatever point this is, it appears as though y squared is greater than 2 to the y. Therefore, that distance is going to have to be defined as y squared minus 2 to the y. Now, how do we deal with these points of intersection? Well, once we've got our brain wrapped around, once we've got our brain wrapped around with the fact that this thickness, this width, quote unquote, is delta y, now we know that we're talking about limits on y instead of limits on x, right? I'm going to call this A, I'm going to call this apparently A again, just kidding, and I'm going to call this point out here C. So I've got A, B, and C. You with me? All right, now watch how we're going to write the integral, and then we're going to play with it and see what happens. The area is equal to the integral from, now we're going to have to bust this up, aren't we? Because we've got two separate integrals. We've got different actions taking place at different places. For the action between A and B, it's almost like you want to twist your head sideways, right? For the action between A and B, y squared is is less than 2 to the y. It looks like a z. 2 to the y. So this is going to be the integral from A to B of 2 to the y minus y squared. Now, what do you think the biggest error that students love to make right here, and it makes me want to pull all the limited number of hairs that I have left in my hair out, in my head, out? They write a dx. It's not a dx, it's a dy. If I take an infinite number of infinitely thin rectangles, this delta y becomes a dy. Now, what does that tell us? It tells us that all our independent variables are y. All of these have to match up. And what are our limits going to be on? They have to be on y. Remember, our limits have to match up with this guy. When it was delta x, our limits were on x. When it became a dx, our limits were on x, right? Now, we've only got half the picture here. We've only got this little sliver. But we have to add in the integral from b to c. And in this case, y squared, for this little sliver from b to c, y squared is bigger than 2 to the y. And we'll prove that here in just a second. And this is going to be dy. And that's it. Now, it's a whole paradigm shift, isn't it? It's like we took the whole world and just blew it wide open. But don't be afraid. Just like when we were talking about functions of x, when one function is higher up the y-axis, then it's bigger than another function. Same thing here. If one function is further right on the x-axis, then it's bigger than the other function. Now, let's use our calculator to figure out this point. This point scares me. We kind of figured out y equals 2 and y equals 4. They're definitely equal, and we're going to double check to see who's bigger in between those. But right now, I know that b is 2 and c is 4, but again, we're going to use our calculator to check. So let's meet over in calculator land. What did I do with my calculator? Oh, there it is. All right, you ready? So let's go to y equals. And let's clear this out. Now, we could do this several ways. The problem is your calculator will not graph functions as a function of x. All right, or excuse me, functions as a function of y. So we actually have to go back to kind of more of an original way of solving these. You could also use your solver in here, but you know me, I like to use graphical methods. So I'm going to go 2 to the x, and then I'm going to hit enter. And then I'm going to go x squared. And this will give it to us in a more traditional way. Now, I do have to tweak my window here just a little bit. I got negative 10 to 10. I don't really need that. Let's go negative 5 to, I don't know, the furthest we got to go is 4, right? So let's go negative 5 to 5. Now, I do need a little taller on my y-max, so I'm going to go to 20. And let's have a really good look-see at these. So if I graph, here it comes. There's 2 to the x, and there you go. Now, it's kind of hard to see here, isn't it? It's a little bit tricky. I could have messed with my scale a little bit more, but all that we really want to do right now is solve for this thing, and then we can use numerical methods to figure out which is bigger. I want to solve for the places where this thing intersects, okay? So we go second calc. I'm going to find the zeros. I'm going to take a left bound. I'm going to get way over here, just so I'm out of my own way. Whoa, I'm going to go left bound, enter, and then I'm going to go right bound. Wait, did I say zeros, you guys? You got to yell at me with that. Let's go second calc. I apologize. I'm getting a little crazy today. Let's try that again. So left bound, and I'm going to put enter in, and then I'm going to go right bound. Oh, second curve, duh. Sorry, not left bound, right bound, but curves. Okay, so it intersects at negative 0.767. Let's write that down. So I know that I'm going to have y equals negative 0.767. So these are going to be my 4 intersections. Let's double check to make sure that it does intersect at 2 as well, and at 4 as well, okay? So second, calc, intersection, which is a 5. And we're going to go first curve, but we got to remember we got to get close to the place where they intersect. So get over there. First curve, I think this will get us close enough. Second curve, enter, don't care about a guess. And I get 2, awesome. And then one more time, second calc, intersect. And I got to get up here a little bit. I got to get away from x equals 2. Otherwise, remember, it'll suck you back to x equals 2. All right, so I'm going to do, whoa, bye. Whoa! Sorry. Let's try that again. I got a little crazy. All right, that's good enough. So let's go enter. Second curve, enter. No gas. And 4, outstanding. Okay, so let's see if we can remember how to double check these things. So this color is officially getting obnoxious. Ooh, let's do purple. So these are my solutions. Now, remember, our thinking was that 2 to the y was greater than y squared on the interval from negative 0.767 up to 2. But it's easy to check, right? If I let y, that's obnoxious, if I let y equal 0, well, doesn't this imply that 2 to the y equals 1 and, or excuse me, 2 to the 0 equals 1 and 0 squared equals 0. So by God, this implies that 2 to the y is greater than y squared on the interval from, what do we got? Negative 0.767 to 2, right? Let y equal, remember we grab a value between 2 and 4. Well, the most logical value is definitely going to be 3. This implies that 2 cubed is equal to 8 and, and 3 squared is equal to 9, which implies that, where are we? Y squared is greater than 2 to the y on the interval from 2 to 4. Awesome. Now all I got to do is rewrite my integrals. Let's open this guy back up. I'm going to rewrite my integrals with my new values in there. Ooh, it appears as though I've run out and they only give you 100 pages. Let's go over this away. I'm sorry about this lavender, you guys. I got to change that. So this implies that the area is equal to the integral from negative 0.767 to 2 of 2 to the y minus y squared dy plus the integral from 2 to 4 of y squared minus 2 to the y dy. And then you can either use your calculator, you can use analytical means, you can use whatever you'd like to be able to solve for that area. Isn't that fun? That's a whole different way of thinking about things too, isn't it? We'll get a lot more practice with this, so don't panic. And they won't take as long. Once you get in a habit, it becomes really intuitive. It just makes sense. And you'll start freaking out a little bit. So I'll see you in class tomorrow if you have any questions for me. Otherwise, have a really good day.